Silpa Kona from the University of Louisville. Graphene is a carbon material that's highly sensitive at detecting chemical gases, but there's a secret to how you grow it that makes all the difference in the world, and she's going to tell us about that secret.
My name is Silpa. I'm from the University of Louisville. I'm a PhD student under Dr. Cindy Harnett, and I'm here to give you a brief introduction about my research work, which focuses on low-cost construction methods for graphene-based vapor sensors. Resistive chemical sensors are being used in the industry for a long time for process control and also for monitoring safety, in addition to environmental protection and also for tracking hazardous materials. So the current existing sensor designs that are out there now, they involve high-resolution lithographic techniques, which are very expensive and consume a lot of time. And this essentially makes it impractical to have low-cost production of these sensors on a very large scale. So our study here focuses on designing and fabricating a device that has a low-cost method for construction and packaging of the graphene-based vapor sensor. Graphene is a two-dimensional material. It's a nanomaterial, and it has amazing properties like high conductivity, low noise, low crystal defects, and a large surface area. So these properties make it very attractive for a sensing element. And so using these properties, we wanted to investigate the electrical and gas sensing properties of graphene in a sensor device, where the principle of operation would be the sensing element, which is monolayer graphene, exhibiting a change in its resistance when it is exposed to certain gases. And when the molecules from the gases adsorb onto the graphene surface, it essentially shows a change in its conductivity or resistance. So to design this device, we opted for acrylic, which is essentially impact-resistant plastic. And this brings down the manufacturing cost for the graphene device. And with each 12 by 12 sheet of acrylic giving about 80 sensor chips, the packaging cost for the acrylic device with the graphene as a sensing element is brought down to less than $2. This slide here shows the schematics for the devices that we've designed. There are two different devices. One is a single channel design and the other is a dual channel design. So from the schematic, there's an inset which shows the cross-sectional view of the device. For the single channel, you have one single gas channel that traverses the length of the graphene layer. And for the dual channel, we have two different gas channels, one for the control gas and one for the analyte gas that we want to test. So in addition to having acrylic as the packaging material, we've also skipped the process of electrodeposition and liftoff of individual electrodes, and we've instead opted for liquid contact ports to make contact with the graphene layer. So this brings down the manufacturing cost even lower for each single device. So when you have the gas that flows through the gas channel, like I've already explained, you have these gas molecules that adsorb onto the graphene surface. So what happens is these molecules, they act as either electron donors or acceptors. So this changes the local carrier concentration for the graphene layer. And this in turn changes the conductivity or the resistance of the graphene layer. This we've seen in both the devices that we've tested out for the single channel as well as the dual channel. The first plot here is for the single channel device, and the second for the dual channel. We can see here from these plots that we have alternating cycles of nitrogen and analyte gas that is sent through the device. So we've tested these devices for organic solvents, vapors, for like methanol, ethanol, and IPA, and all the three different plots are shown here. So you can see that when there's nitrogen in the system, it establishes a baseline resistance, and when it is switched from nitrogen to an analyte gas, the graphene layer instantly responds. You can see the change here, and when the gas is again switched back from the analyte vapor to the nitrogen, the signal recovery is spontaneous. In existing designs, we usually see that the sensor has to be exposed to either UV radiation or it has to be heated or annealed to bring the sensor response back to its baseline resistance. But we don't see that in our devices. So the signal's recovery is spontaneous, and we have response times about tens of seconds in both the devices. So, and we have more data